Hi. I hope you're following up our last session where we introduced the 3 to 5 big assumptions of regression models. So, what do we do with those? As you can see, I have opened up a file where I've pasted in all of the code from lesson 10. All of this code is right there. You can do it all on your own and should. I'm going to walk through how it works. So this lesson uses the example of 1,000 credit reports. Each row in the data frame is a different customer who has a credit report. The outcome variable is going to be the amount of debt that they have, and their predictors will be certain traits about them. We can get this data frame by loading not just the tidyverse package, but also the ISLR library right here, which is a great package that some people used for teaching data science. We also need to load the CAR package, which is really useful because it has our model assumption tests in it. Okay, so we're going to use the credit data frame, which is stored in ISLR. We're going to import it, renaming some of the variables to better things. Don't worry about it, just run it, it'll be fine. And once we do that, we can see that we've selected their ID. And let's take a look up here and see what exactly our data frame has provided. Okay, so we see, great. We see each row has an ID number, how much debt they have in dollars. So this person has $333 in debt, but their credit limit was about $3,600. That means the maximum amount of stuff that they could spend on a credit card. Okay. Their income, I believe this is in 10,000s, and their age. Wow. Pretty good income. Maybe that actually is in thousands. That would make more sense. 14,000. I don't know. Okay, so main point. Let's make a model of this. We can predict the amount of debt that a person takes on average, given their credit limit, how much they were able to take on, given their income, and given their age. And we can save it in M, which can, as we've talked about a lot, you can do this using an equal sign or using an arrow. Okay, great. So we've saved the model in M. You'll notice that it's showed up right up here. We can run that summary function, and let's take a look at our model real quick. Okay, what can we tell about our model? So we've got our model equation. We've got the distribution of residuals here. We've got our beta coefficients for each variable. So for the intercept, alpha, we know that on average, independent of everything else, you're just going to start off with about a debt of minus $300. So that means that most people start off not in debt. Obviously, this is more of an expression, right? It's not actually how things work. It's just the intercept according to the data. Okay, credit limits. As your credit limit goes up by $1, you get about $0.2 more in debt. As your income goes up by $1, or by, I guess, $1,000, we decided was the unit, you get $7 fewer in debt. And as your age goes up by 1, you get about $0.8 less in debt. Okay? We can see that all of these had statistically significant effects, except for age, so I wouldn't be too confident about that one. But it's a pretty low p-value. we see that our model has an R-squared of 0.87, which is huge. That is a really good model. And we see our F statistic is pretty high. It's way bigger than 0, and so it has a very extreme p-value. So that's pretty significant. By the way, you'll notice this p-value a lot. This is what happens when you have a really, really, really extreme one. It says that the p-value is less than the smallest value that R can produce, 2 to the negative 16th power. Okay, so we've made a model. We've interpreted the model. Now we want to test, do our variables have linear relationships? Do we fit the assumption of linearity? So we can do this in a couple different ways. For instance, here's one way that isn't written. Let's see, our data frame is called reports, right? And so we could just, for each variable, go like, okay, ggplot, mapping equals AES, x equals, let's do credit limit first, and y equals debt, because y is our outcome. And we are going to first use geom point, and we're going to use geom smooth to create the best fit line. And we're going to say method equals use lm, and please don't worry about giving us a standard error confidence interval. Okay, so if we run this, we get a plot for one of our variables, and we can see that, yeah, that's a pretty linear trend. It is possible that these aren't going to be linear, that there will be no trend. That's fine too. But what we don't want is for this to be like clearly an exponential trend. If it clearly goes, instead of straight, but goes like whoop, very curvy or something like that, that means that we should be modeling our data differently. Okay, so this is, it's a pretty linear trend, or it's not a trend at all. So that's good news. Okay. Remember how we learned pivot longer back in week 4? Pivot longer comes in really handy right now because it lets you take predictors, show the outcome for each of them, stick them all in a column, and then facet plot them out. If you want to see what I'm talking about, we can run this thing called pivot longer. Okay, so what this does is it takes our reports and it stacks them together so that each individual actually occurs multiple times. Let's check this out. See, so now we have the debt level paired with the credit limit level for each individual person. We have the income level under value paired with the debt level for the same person, the age, okay? It's put them all in a nice tidy data frame, which becomes really helpful all of a sudden to show those linear trends across all 3 kinds of data. See what we've done? So you could do this individually using the tools you already know, or you could use pivot longer to restructure the data and then visualize it all at once. These are 2 options, but you could also do it just the way that I did it right here, which is what we learned about 3 or 4 weeks ago during the correlation week. Okay, so we can see, yeah, these are pretty linear trends. There's nothing exponential happening here, nothing like loop-de-loop happening either. Okay, so we can feel pretty confident that a regression model is good for this kind of data. So there's another way, there's another thing that we should do. We should check if any of our predictors are correlated. How might we do this? Well, we should probably, we could get the correlation between each predictor. Now, When you've just got like 1 or 2 variables, that's fine. That's like 3 or 4 correlation tests. But when you've got many, many predictors in a model, that gets old real fast. Here's a really quick solution. We could run this code right here, which says, hey, please grab just these numeric variables, right? Because we can't do correlation on something that's not numeric. And now, using that, use this function called core, which comes with R, and use only complete observations. So it's kind of like na.rm equals true. And we're going to generate this correlation matrix down here. It's really nifty. So you'll notice if we read this, so the correlation between debt and debt is 100% because they're the same. The correlation between credit limit and debt is pretty high. Correlation between income and debt, age and debt, great. So that's useful. But what we really care about is credit limit, one predictor, correlated with income, another predictor? And it does appear to be rather strongly correlated. And it doesn't appear to be very strongly correlated with age. But there is something going on right here with credit limit and income. So that makes me wonder, maybe there's some multicolinearity happening in our model. Well, good news, there's a really fast way to check. We can use the Vif function. Personally, I just jump straight to the Vif function, but correlation matrices are another great way to do it. Okay, so I'm jumping straight to the Vif function, which works like this. You could also write it with a pipeline like that. Of course, for that to work, you'd have to load the tidyverse package, right? Okay, so let's run it. And actually, I'm just going to make things look a little prettier here. Okay, we got numbers. Vif gives you a series of numbers. Each number is paired with a predictor. This is the variance inflation factor for credit limit. This is the variance inflation factor for income, and this is the variance inflation factor for age. They're really useful because they exist on a scale from 0 to infinity. And generally, if your value is from 0 to 2.5, great. They are not collinear, not problematically so. If they're from like 2.5 to 5, okay, like there's a little bit of interaction going on here, but it's not gonna like end anyone. It's not gonna be a big problem. If you have a VIF over 5, you should be a little skeptical. If you have a VIF over 10, you should be like, oh my god, I do not trust this model. This model is completely bonkers, right? Generally, my rule of thumb is I keep all of my VIFs under 5. And I really, really try to keep them under 2.5. Let's say that I was deeply concerned about income. The appropriate, because it's 2.75, don't worry about it. That's a very good value for VIF. But if we were concerned, we could take that predictor out. And that would take care of the multicolinearity problem. Okay, so that's how we deal with multicolinearity. There's one more test that we can use. First of all, so remember how we have 3 more assumptions: independence of observations, normality of residuals, and constant variance of residuals, which means homoscedasticity. We can test all of those at once by testing the third one. We can say like, hey, do our residuals tend to vary at different levels of the predictor, of the outcome? The non-constant variance test does this real quick. So let's run it. Let's see what happens. Okay, cool. So they try to evaluate do our residuals vary a lot depending on what the outcome was, and we've got like a pretty medium chi-square of 0.58. So, and it generates a p-value too. Okay, great. So is this p-value significant? It's p equals 0.44. P is way bigger than 0.05, which means we can be pretty confident that there is not heteroscedasticity in this, that there is not non-constant variance. We can be pretty confident that our data is, like pretty normal. We can also, if this test is a little confusing, you can also assess it visually. You can try to assess, are our residuals normal? And the way that we would do this is by plotting a histogram.